And hello, we can start. And welcome to this webinar, Fundamentals of Circuit Breaker Testing and Agile Solution. The first of the two parts about circuit breaker testing. I'm Mary, Marketing Manager for Africa, and very happy to welcome you today as the moderator of this presentation. I will be supporting you on technical issues and questions for our presenters. I have the pleasure now to introduce you Stuart, Product Manager for SearchTech and our distributor partner. Thank you very much, Stuart, for being here, and please say a few words about SearchTech, your services, and our collaboration.
Morning, everybody. As Marie-Claude explained, my name's Stuart Ashton. I'm the Product Manager for Test and Measurement and Safety Products at SearchTech. We're proud to be business partners with Mega, offering specialist products, which include transformer testing, circuit breaker testing, and relay testing. We also offer facilities for repair, recalibration of low, medium, and high voltage product. We offer safety, as in earthing, as you can see from the picture on the right-hand side. We are SABS approved with some of the products. We also do an extensive range of ARC-rated PPE. And if you have any questions, please feel free to ask them at the end of the webinar or during the webinar, and I'll hand you back to Marie-Claude.
Thank you for this presentation and all the great job you are doing with Mega Solutions. So, on the right of your screen, you should see a control panel similar to this one. You can submit questions at any time during the presentation by typing it in the box highlighted in red. The questions will be answered at the end of the presentation during the Q&A session just before the demonstration. And also at the very end of the webinar, there will be another time for a Q&A session. If we do not get the time to go through all the questions, they will be answered directly by email. And as well, at the end of this session, you will receive a survey where you will be able to raise questions and give us precious feedback. Last thing is that this meeting is going to be recorded, so you will have the opportunity to receive a copy of this webinar. Now, let's start by presenting you Bull, our application engineer, and please have a nice session with her. And Bull, I'll give you the hand.
Hi, yeah, my name is Bull Ekberg. I'm the application specialist in the factory in Sweden, Mega Sweden. I've been working here for more than 20 years now, and earlier I used to work with ABB and Bombardier. And today I'm going to talk about my favorite subjects for circuit breakers, and of course testing, and our instrument we use when we do these tests. So I'm going to start my presentation now, I think. So I'm going to show you my screen and go over to the presentation. So today we are going to talk about the circuit breakers, the testing, and the instrument Eagle, which we use for medium voltage circuit breakers. So we're going to focus a little bit more on the medium voltage breakers today. So I'm going to start talking a little bit about the different types of circuit breakers and go further on with breaker parts. And of course, we're going to talk about testing, the general tests and specific tests for medium voltage breakers. We also have some special difficult test situations I want to mention. And after that, we're going to have a question and answer session. And then we're also going to have a small demo with Eagle and a medium voltage breaker. And again, after that, we're going to have questions and answers again. The breaker, yeah, it is in the middle of a whole network. And it's an odd object. It has very different demands. During normal situation, when it's closed, it's the almost perfect, the really good conductor, which are supplying through the breaker to the network and users. But when it's open, it should have totally the opposite work. It should be the perfect insulator. And the function is that it has to be a part of a protection system because it is protecting the lines and transformers, the really, really expensive parts and important parts of a network. And the special function here is that the breaker needs to be able to open up also under fault conditions. So if you test your relays and they say it's an overcurrent or a fault, the circuit should be able to open. So if you don't test your circuit breaker and it's not opening, yeah, what's the point of testing your relay? So you have to make sure the whole system is working to have a proper protection. I'm going to look at some different types here. This circuit breaker can be called many things. One thing is the name, of course. It's a Hitachi made as ABB VD4, and it has been a common type for many, many years. Another way to describe it is a three-phase withdrawable circuit breaker, 10 or 20 kV, and it's a vacuum breaker. So it has vacuum around the poles. Here is a total different type of breaker. This is quite an old breaker. It's an air pressure breaker, and it's a bit special because it has also a disconnector mounted at the circuit breaker. And these two, the disconnector and the breaker poles, they need to be synchronized. So when you test one of those, you actually have 2 breakpoints per phase to measure. So this is a really special one. And this kind of breakers are quite noisy. Here we have a one-phase breaker. This is on a HVDC station. And to the left, you see the single pole. And to the right, you see the other side of the breaker, the mechanism with a spring mechanism. You can see the spring here to the right. Here is also a very special object. This is a SF6 switchgear medium voltage, where you have no access to the phases. Normally, when you do measurements, you connect at the phases and have the circuit breaker disconnected and grounded. But here, you don't have this access. So we're also going to look a little bit at this kind of solutions. And this is a Siemens breaker, as you can see, and also a medium voltage switchgear. A little bit higher voltage, but still in like distribution level. You have a 66 kV station here, actually in Mozambique, and it's ABB breakers as well. And here you see that they have grounded properly. You see the groundings just in front of the man there. And it's a normal 3-phase breaker. And this circuit breaker has what we call a common mechanism. We're going to talk more about that later. Here are some bigger breakers, and as you can see, they look totally different. From my first look, I would say, oh, is that a transformer to the right? No, that's a dead tank breaker. It's an American type of breaker, which are very handy if you have problems with earthquakes, because it's much lower, so it doesn't fall over like it's easily done with the other types of circuit breakers. So they use them in US and also some countries where it is common with good contact or earlier good contact with US. To the left, you have a circuit breaker which has 2 breakpoints. When you come up of higher voltages, sometimes it's not enough with 1 breakpoint, so you have more breakpoints. And in this picture, you only see 1 phase. And this is also higher voltages. This is a GIS, a gas insulated switchgear. And as you can see, it's very hard to access anything. It's covers, is like covering everything. So that's also is a tricky object to measure. Here you can see another type. It's an ABB circuit breaker or switchgear, and you can see that they have removed some of the covers to show us the interior. And there you can see that all three faces are in the same pipe, in the same cover enclosure. That is not always the case, but normally on lower voltages, they are all in the same compartment. I mentioned the poles and I mentioned mechanism, and I talked about springs. Yeah, how are we going to look a little bit more in detail on that? To the left, you have a normal outdoor circuit breaker, a distribution level, and at the top, you can see this, the connections, and underneath you have the pole. And down here, you have the control cubicle and the common mechanism. It's one mechanism for all three phases, phase 1, 2, and 3. Here we have a picture of the interior, and that tells me this is an SF6 breaker because it has this kind of pole. And here you have a photo of a similar one. And the breaker here has two parts, one upper fixed and one lower moving part. And those also have two parts. We're going to look at that better on the next picture. Below here is showing the mechanism. And what's important to look at here, I would say, is the two springs. You have a blue spring here at the bottom and a red spring. The blue spring is the close spring, which making the breaker close. And it contains all the energy actually also for the open. But when it's closing, it's giving the power over to this spring, which is the open spring. So it contains the energy to do both operations when it's waiting for a close operation. The chamber, the pole, is common with SF6 today, but this can also be filled with other gas, oil, or it can be a vacuum chamber. And this is inside where the contacts are placed. Underneath here is isolation to earth, and inside here also goes a mechanical link down to the control. Here is the control cubicle, and it contains down here the operating mechanism, the trip and close coils, which are controlling this spring mechanism, and the auxiliary contacts. We're going to talk about these parts more later. It also contains the spring and the spring motor. You need a spring motor to charge the operating springs. And this, as you see, is only shown in one phase. Here is another example of a contact. This first contact here, the copper one, is a vacuum breaker. It is two plates which are moving. One is moving to the other. So this one goes into position and then it stops. When you talk about SF6 and also oil breakers, they are different. They more go into position. They have a contact touch between these two, and then this part also goes in contact. This part is fixed and this is normally moving, and here is the arcing contact, and this side over here outside on both sides, all the way around actually, is the main contact. So when it's in position, it goes all the way up to the bottom here, or up to the top, you could say, right? But as I said, SF6 breakers has a main contact and an arcing contact on each side. And here is another vacuum circuit breaker contact, and this breaker actually turns also when it moves together and separates. Also, that's an easy way to open the breaker to not get any arcings. And another example of an SF6 breaker, you have the inner part and the inner part here, and the main contact here and here. So this is in good shape. When this is not in good shape, you have a lot of, it looks like a pattern here. It gets worn out. So when this breaker closes and opens, you first have contact here inside, and then the main contact. And the important thing is when you do an open, the other way around, when the main contact releases, there is still current flowing through the arcing contact. So the arcing contact can take care of opening. So it's the whole purpose of this contact. And this way it has also a higher resistance, so the current gets a little bit limited. And of course, you have SF6 gas as quenching gas. Here you see a circuit breaker which has been in use, also SF6 breaker with main contact and arcing contact, and the two different sides. The SF6, yeah, it's an inert gas, so it's really stable. They're using this gas just because of that. But there are some problems with it. It's a heavy gas, that could be good to know, and it mixes with air very fast. But it is a greenhouse gas, and it's a really bad one for the environment. So when you have this kind of breakers, it's important to also check the gas containers that they are not leaking continuously. And if there has been an accident, it's important to not touch any leftovers from the gas, because it gets like acid, highly corrosive material from the gas when it has gone through openings and trips. We go over to the parts in the control cubicle or mechanism. Main contacts, okay, that's where the current flowing, that's the normal, the three phases. But auxiliary contacts, yeah, it's a type of almost like relay contacts for control purposes. You have them in the circuit of a control, but you can also have them for indication and for other purposes in the switchgear. And you can see them here on the picture, and they are directly linked, see that also in the picture here, into the main contact. So they are either showing the same position as the breaker or opposite, but they can also be a little bit both before and after. This kind of things you have to check in the user's manual and the diagrams, because they make them a bit different, because they need to work together with the circuit breaker coils. And they are there in this coil circuit to protect the coils. The coils are so important for the operation, so we protect them. So we can't send the pulse to a closed coil. The circuit breaker already is closed. And as I said, there are different types, and we call those different types A and B. And A is the type which are following the contact, and B is the one which is opposite. And here you have what people fear, I think. This is a part of the circuit diagram. And this is a part of the control part. So what you can see down to the left here is the close and the opening coils. And the opening coils are even two. You have trip 1 and trip 2 here. And you can also see here the motor. Go and paint this part of the circuit diagram to make it a little bit easier. Here you go through the different parts and you come to the auxiliary contact. So now you are in the position you can close the circuit breaker, and here is the closed coil meeting the minus. Here you have an open circuit, you have an auxiliary contact A, so it's open, so it can't open the breaker, and you go to the coil for trip or open. and again meeting the minus. So that's also symbolized here with this B and A contact. You always draw these diagrams as in open position when they are not energized. So that you can always know that this is when the circuit breaker main contact is open. That's how they draw these diagrams. The mechanism, yeah, you have different types here. One of the most common ones is the spring mechanism. At the bottom here, you see one with disc springs, so this is a bit unusual. Maybe not unusual, but if you look at all types of springs in the world, I would say the disc springs are not as common as this kind of springs. When you think about a spring, you tend to look at this kind of types here to the right. But they can also be operated in other ways, circuit breakers. They can be hydraulic, pneumatic, magnetic, and also motor control, that is directly the motor controls for operation. We are soon here going to talk about different types of testing. And when you talk about testing, you must think about what you want to achieve. What do you want to see? Where is the problems? And SIGRI helped us there. That's a French organization which makes reports regularly. Every now and then they update these figures, but they tend to be quite the same. The faults are in the mechanism. So we should consider this when we test. There are many users out there that only test timing, and that's a bit limited because then you don't see all the faults in the mechanism. And it's actually there we can expect the faults. As you see, the interrupters is less than 10% of the faults. So we should look at testing also to test the important mechanism. So what kind of tests should we do? Of course, you want to check the resistance because the circuit breaker should be the perfect conductor when it's closed, right? So you close the breaker and test that. You want to look at timing of main contacts when it's opening or closing or multiple operations. You want to look at the timing of the auxiliary contacts we were talking about. And you want to measure the coil current. Another test you should do is the minimum voltage test. You should check that the circuit breaker operates also when the battery is not at its best. And to cover this with the operating mechanism, I really recommend to do motion tests. And it's also good to check the spring motor. So you measure the spring motor current. The contact resistance measurement, yeah, other people may call it doctor test, DLROs, MOMs, micro-ohm, SRM, static resistance measurement. But it's all the same. You measure the resistance when the breaker is in normal closed position. And to do that, you should use a high current. And IEC says minimum 50 amps. And the American standards actually says 100 amps. So 50 amps, I would say, is not a very high number here. We should really at least use 50 to test circuit breakers. So what do? We send a current over the contact and measure the current and the voltage so we can calculate the resistance. And this is to verify that we are not going over the max contact resistance measurement, which you find in the manufacturer's report and also in the manuals usually. You inject the high current and you should use a 4-wire method. You should have separate cables for current and separate for voltage. And this is possible to do both sides grounded, which can be really good and nice to do when you're out in the field outdoors, because you have very much problems with inductance or actually capacitive coupling. So that would be a much safer way to work. And what do you want to look for? Yeah, what you're looking for are these different force contacts which are in bad shape. They can be contaminated, they can be eroded. You can have loose connections, as soon as a connection is wrong, also outside the breaker, then the resistance will increase a lot. But also the contact pressure and the smoothness of the contact. So you really want to have the whole area in contact. I often get the question, but what is normal? Well, that's a difficult question. When it's modern breakers, I would expect it to be less than 30 microohms when it's a normal distribution circuit breaker. But it's really depending on the type, how old it is, and also where you can connect. If you connect, for example, on a GIS, you will be measuring a lot of things in the circuit, and you will maybe end up with 150 microohms, and that can be totally normal because you can't access direct at the circuit breaker contact. But a normal modern breaker, really low values. And if you don't have the values, compare between the phases, compare with another circuit breaker of the same type. Comparison is something really important to work with when you work with circuit breaker testing. And normally you have more than one breaker and normally more than one phase in a station. But also these figures you can find in the manufacturer's material. Okay, timing, yeah, it's the same thing there. Look for the figures in the manufacturer's specifications. If you don't have anything, compare, not only within the different phases, but also similar types of circuit breakers. And the problem is here, you really need to have quite detailed figures. We come to that. And what you do, you check how long time it takes for it to open and to close. And you also do multiple operations to see how the circuit breaker reacts when you connect it towards a fault. So instead of just doing close, open, I would do free close, free open, and I would also do a couple of CO operations, for example. How do you do it? Yeah, the classic way is to put about 25 volt DC over the contact and check when there is a current flowing or not. When there is no current, of course, the circuit breaker has opened. And you connect cables with clamps over the contact. And of course, when you do this, you have it disconnected from a network. In this case, it's withdrawn, so to the left, and outside, you have to disconnect to the disconnectors and ground. And to the left, you don't ground, but to the right, you need to ground at least one side. And it's, of course, safer if you can use two grounders with dual ground technique. So what's the demands? Yeah, of course, you follow what it says in the specification. And if you have good shape tested breakers, you have a reference. But you also need to check the synchronization between the phases. We talk about 1/4 of a cycle, so that's like 5 milliseconds at close operation, and 1/6 of a cycle at open operation. So you see the demands are higher on the open operations. So even though it looked okay, if you compared with the specification, it can still be bad when you look at the demands from IEC. Then if you have bigger breakers, you also have to look within phase, and there the demand is even higher. Because there is a reason why they put more than one brakes per phase. If you have two breakpoints per each phase, it's because they're both needed for operation. So especially, of course, when there is a fault. Auxiliary contact timing, yeah, we'll be talking about that. Control contacts in a coil circuit. And they are important so you don't burn this really important inductive coils. And they're also measured with 25 volt DC, but connected with the atto terminals. Okay, coil current, yeah. That's something which normally measured automatically in an analyzer today. So you measure the current needed for the operation in the coil circuit. And it reveals detailed information, really useful. It, of course, detects problems in the coils, but it can also give you information about the supply and details about parts of the mechanism. And the best thing you could do here when you start is to work with comparison. Compare with similar circuit breakers, the same circuit breakers, the actual same unit, and make sure the whole part, the whole graph is the same. Here we have somebody who looked at this in detail. That's one of my colleagues from used to work in Canada, and he really went through this in detail. So we start at number 1. That's where we send the pulse. The first thing the coil needs to do is to get magnetized. So first, it's just an electricity thing going on. Nothing physical is moving on more than this current flowing. And then you start to have the armature travel. So that's where the mechanism motion sort of starts. And that pulls the energy to release the spring to do the work. Then it's raising up to the maximum, and at 7, the auxiliary contact releases the circuit, and you have a decay or demagnetization of both the coil and the whole circuit. So of course, if something happens really at number 1, it's not really a problem maybe with the coil. It could be like supply. If you have a problem at 1 or 2, it can't really be the other parts of the mechanism. It must be the supply or the coil, which is the matter. So already here you can exclude some problems. The minimum voltage test, I mentioned that short before. You must verify that the breaker operates at the minimum voltage. That's according to IEC as well. And this you have to do because it's really important to know that the breaker still operates, even though you have a tough job on the battery, or maybe you lost a few parts of the battery or a few cells, or you have a big break fault in the station and a larger breaker has operated, but you still need to operate your breaker. So closed, the demands are not as high, but at open, you must be able to operate even within 70% of rated voltage. And this is also a way to like provoke a fault. You will see faults on the breakers earlier if you try to test them with a low voltage. Here we have a little measurement on a breaker with a very low current. So the coil current, the red one here, is not looking so very good. But this is the normal operation for the circuit breaker. But to the right, we have tried to operate with a lower voltage, and it was not enough voltage for operation. So this breaker was not in such a good shape. So it never moved, the motion never changed, and the current didn't show the normal trace, and we didn't get any timing trace. And I could mention here that the timing traces is the red, yellow, and the blue to the left, and the red is the current and the green is the motion. And if you compare with the right, the only thing happening is the coil current. So here you can say this is not enough energy to operate the circuit breaker, and that is because actually it's too weak and too bad shape of the circuit breaker. Okay, to cover this thing, to measure more, what should you do? Yeah, we should measure motion. And to do that, you need a transducer and you need analog or digital inputs on the analyzer. The transducer types in general are rotary or linear. You can also have magnetic types and optical ones. Optical is a problem here because the speed is really fast and acceleration is really fast. So I haven't seen any good examples of that. But to measure, you either use these digital incremental types or analog. And here down to the left, I show you a mounting kit for this transducer because you have to get the transducer in position. So at the right, you see a circuit breaker with a link arm and a white holder and the black transducer in the middle. in the white holder. Here is the transducer. And this is a rotary one. Here we have the VD4 again, the breaker we looked at in the beginning. And again, we measure motion during the operation. And either you measure like here, we connect directly at the pole underneath, or at a rotating point or linear point in the mechanism. And another important thing to measure is the damping. When you measure motion, you look at some certain things when you analyze. You look at speed, and when you look at speed, you need to look at two different points to get a slope. So you're calculating the speed here, and this is calculated automatically. You also get results as over travel and rebound, how much it's moving before it goes to steady state, because here are the steady positions for the circuit breaker. Here the breaker is closed, and here the breaker is open. And between here, we have what we call a stroke. Here we're also showing the timing graph. So we start here to the left, the breaker is open, and the breaker closes. And over here, it opens again. So what happens? Yeah, first you have a coil current thing going on, which is not shown here. But then after the basic, it has released the spring, it starts moving. And here you have a contact closure, and this is where you normally put your first speed point. And then it does a small over travel, and then it's static in the closed position when you again have started to open the circuit breaker again. You start moving, it release, and you have something called the arcing zone. So that's where you have a really important speed. You need to have a right speed in this zone. Down here, you have a new calculation point, and in the bottom here, you have a damping zone. And this is one way to look at damping, but there are also what we call dash dot, which I'm looking at here, dashboard to the right, which is an ABB type of damping measurement. But this should not continue forever, and it should not do too big changes here. And again, good to look at either specifications or footprint or reference measurement. Speed and motion is also measured as travel, stroke, and as I mentioned, also damping is a type of motion measurement. Here we have a couple of mountings. We have the mounting here on this picture is the same here. And at the point, we have put here an adapter to then measure with the transducer, the black, and the picture to the right, the black dot here, round transducer. So what do we want to look at? Yeah, we look at the speed. The speed needs to be correct. Of course, it should not be too slow. Then we won't manage to distinguish the arc. But it should also not be too fast because it can get mechanical damage. And the contact stroke, it needs to do enough motion so you get the correct brake capacity and isolation. But it should go also in enough contact, deep in contact penetration, so you get the whole main contact touching the other part. And damping dynamics, if there is no damping, there's risk of mechanical damage, and if the damping is too hard, the breaker might become too slow in the arcing zone, and then you don't get a proper extinguish of the arc. And there's also a problem that you can get that it rebounds, it connects again, and then you can get a really bad arcing situation with explosion, because then all the gas is lost in the circuit breaker, all the pressure is lost. Not lost, disappeared, but the pressure is lost in the circuit breaker. So it needs to do correct on the first try. You can't try to open again because the mechanism is still running. It needs to do a direct open. So why do I measure motion? of course, to find the faults, right? And apply to the standards, both IEC and IEEE demands this. And you want to get this really important information about the circuit breaker and its condition. And you collect data so you can compare. So if you have a new breaker, it's good to take a measurement already then, so you have a good reference, and also to know that you have the right thing delivered. And you want to discover this kind of problems early so you don't get explosions or other catastrophe damage. So what I'm trying to tell here, the timing and coil current doesn't tell the whole story. So to do this mechanical test is the way to fully reveal the problems in the circuit breaker. I have an example here. This circuit breaker has operated correct in phase A and B, and the timing looks fine on A, B, and C. Actually, you have a good result on the timing. But if you look at the graph over here, the red and the blue is very similar. But the yellow looks different. So already this, that it's different from the other types, should really make you observe it. So all three phases trip times were in specification. The difference between the phases were well within the specification, but when we measure the motion, you could see this really large over travel, the yellow. So the timing indicates that it's okay, but the motion reveals a serious issue with the circuit breaker. So if this motion measure had not been done and this fault we would not have relieved, then you could have a really serious fault failure in service. Motor current, yeah, this is only measured, of course, when you have a spring mechanism. So you measure this with the current clamp, and you look at different changes. You look at the max motor current, and this vary with winding resistance, the supply, and applied. And the start current is not what we're looking at, but more the continuous data. And motor voltage, also that you look at, and the spring charge motor start time, the closing time of auxiliary contact for the spring charge motor, and also the stop time. So increased time, then you have a higher mechanical friction. And here you have one of those examples. Another thing you must notice here is that normally when we talk about operations of circuit breakers, they operate within 25 to maybe 40 milliseconds. But when you measure, you don't have to measure so long time. But when you measure the motor current, you need to do another measurement time. And this is quite a short one with 12 seconds, but they can be up to maybe 20, 25 seconds. So it's a totally different measurement. You need to measure the whole motor time. Then you have some specific tests you do on medium voltage breaker. It's very common with vacuum breakers on the medium voltage breaker. And these kinds needs to be tested for vacuum integrity. What you do, you put a high voltage over the open contact and make sure the dielectric strength is okay. So it's a simple go, no go test, but it doesn't replace the timing and the coil current test. This is an extra test. You connect clamps over the contact and just expect a green lamp when you turn the knobs. And for this, you use the instrument VDAR. Small light instrument, like 7 kilos. So quite convenient to work with. We looked at medium voltage breakers which were difficult to access. Yeah, we have some air insulated and gas insulated switchgears where you can't access the main contact. And some of these have an outlet called VDS. There are a few examples here in the picture. Vega here, and another type here, and the third type here. And here you can see a VDS accessory. So you can use this to measure the timing without connecting at the main contact. But to use this, you need a bigger analyzer. You need Team 1700 or Team 1800 because you need analog channels. You need 3 channels to measure this. And here is an example how it can look like. You get results as result list, but also as this graph. So this is an opening. So what this capacitive outlet give you is actually the sinus, of course, of the from this voltage transducer. And when the breaker is opening, the voltage is disappearing. And that's the instrument convert to a result list. And this must remember that the circuit breaker here is in use. You have a current and voltage in the switchgear. So it can be good to operate with a delay, and then you can move to a safe distance. For the normal types of circuit breakers, the main parts, Eagle is a good solution for this segment. Medium voltage, distribution breakers, as long as they have one mechanism and only one break per phase, so 3 phases. And it's really convenient also because it's 7 kilos and really easy to use. And it can be run standalone and with PC. And the video with the demonstration we're going to do here is Eagle with a PC. But if you work standalone, it also has a built-in printer so you can get out the result directly. Contact resistance measurement, yeah, that you also want to measure. And here I recommend the MOM2, small held unit, less than 1 kilo, and up to 220 amps. And that also, of course, depends on what you measure on, how high resistance is. And you work with these Kelvin clamps. And as you see, we are using this 4-wire method. We have current cables, black and red, and control separate voltage cables. For the minimum voltage test, you need a voltage supply unit, and this can also, of course, be used as normal power supplies during normal tests, normal with the analyzer, and it can supply both AC or DC to the coils, and has a separate output for motor supply DC. Okay, that was the presentation part. So we are going to have a questions and answers session here. Marie-Claude, have you received any questions?
Hi, Bull. Thank you very much. Yes, indeed, we have some questions. So the first one, is can all these tests be done like on CBA 3000 test kits?
A CBA
3000 test kits.
Ah, then you got me. I'm not so familiar with that type. I know there are different CBAs, but that's one of the smaller ones from what I know. I'm sorry, I don't have that answer. I think you have to look at the specifications from that manufacturer.
Okay,
but I think that's one of the small ones from that manufacturer, I think.
And then this question could be answered by email as we got your email, John. And he has also another question, which is how often should all of these tests be done, or what informs each test? Or what informs, sorry, each test?
When you should do the test, that's a difficult question. Actually, when you look at like nuclear stations, for example, they test like every year, but of course they are really, really important circuit breakers. So it's a little matter of how important your breaker are. But I would say, at least I would say test every 5th year. But the thing like this vacuum test, I would say if you move a circuit breaker, then you should do this kind of test, and when it's new, right? If it hasn't been any extreme situations, maybe you don't need to do the vacuum test every 5th year. But if you transport a circuit breaker, for example, you can, of course, understand that could be mechanical damage to the pole, and that's important to find before you put it into service again, because it can explode, right? Because it doesn't have a right lack of gas, so sort of the vacuum. It has to be intact. But somewhere between 1 and 5 years, depending on how important your breakers are, right? Okay.
Yes, we got some questions before switching to the demo. When testing motion measurement, do you have an equipment to test the spring tension?
No, not like directed spring tension, but it relieves when you do the spring current test, because it's motor test, because of course if you don't have pressure, it will get sort of, if it's too weak, it will get charged too quick, right? Because it just won't have any pressure to give to the motor sort of. So I think you're going to see this when you do this motor test.
Another one, well, the last one before the last Q&A session at the end of the webinar is, what does the contact resistance value really significant? And those warrant alert for user to look into it for different type of gear.
Sorry, I didn't fully hear your question there. What the contact resistance?
Yes, what does the contact resistance value really significant, and does warrant alert for user to look into it for different type of gear?
In general, when there is a real fault on the circuit breaker, this value tend to rise quite high. So if you expected 25 and you get 50, that could actually be a breaker in perfectly good conditions. But if you get like hundreds of microns, then you're like, that's a totally different story, because if you get high enough, it's more or less a heater of a circuit breaker, because you have such a high current flowing through it. But it needs to be low, like normally I would say under 100 microns on a normal circuit breaker. But if it's an old one, those figures can really, really vary, right? And that's what can be faulty. It can be dirty surfaces, it can be bad contact pressure, but the most common fault there is that people have done a mistake, because when you connect this current and voltage sensors, they need to be in good contact, because otherwise you're measuring the resistance between the clamps and the object. And if you, for example, have a painted object, it's really difficult to get a good contact. So you really have to make sure you have a good contact when you're measuring, because that's actually the most common problem, that you have done a mistake while connecting.
What do you make of cases where the contact resistance measured in the nano-ohm range?
Nano range, okay, never experienced that. What I know is like that generator breakers are much, much lower, but we haven't really talked about this special circuit breakers. I expect that must be some kind of circuit breaker which would be nano. It sounds like somebody put a wrong figure somehow, that you have set the system wrong somehow. To me it sounds wrong. But I'm not like the world specialist on contact resistance measurements. But yeah, of course, DC breakers, generator breakers, that's different stories, right? I'm more talking about this normal distribution and medium voltage circuit breakers here.
Okay, perfect. Then we will keep all the questions for the Q&A session at the end of the webinar. But please maybe introduce the demonstration.
Yeah, I want to mention a few things here. What we don't talk about in the video is that, of course, when you work with objects, you need to follow the local safety instructions and work in a safe way with disconnectings and groundings. The video is in a controlled environment here in our training room. So, of course, here I don't ground the circuit breaker sample. And also when you connect motion transducers, make sure that the circuit breaker is not charged. So the spring should not be charged, because then you can get an operation by mistake and damage your hands, because it's a very strong power in those springs. So that was just a little bit of a caution message I want to tell you. So take care of yourselves when doing these kind of measurements. Think twice, right? So let's start the video. Gonna see me measuring on a medium voltage circuit breaker.
Eagle is a small timer which can do timing, motion, and also measure the coil currents. Today, we're also going to use B10E, which we need to supply the coils and also the motor charging. We're going to measure on the circuit breaker Sacha. It's a 12 kV medium voltage breaker. It has 3 phases, the upper and the lower contacts. It has a motor mechanism, a common mechanism for all 3 phases. I'll start with connecting the plus and minus of the motor charging on the instrument. Plus and minus. I connect plus and minus for the motor on the object. I continue with connecting the coils. I need the supply, plus and minus for the coil. The plus creates the pulse, so that goes to the instrument. And we need to meet with a minus on the circuit breaker. I connect the pulses on the instrument, close, and open. And I continue on the breaker. Close and open on the breaker. I connect the timing leads, main contact, and connect on. I connect the main contacts, timing, 1, 2, and 3 on the upper contact. 1, 2, and 3 on the lower contact. Since the cable only have 4 connections, I need a normal sense cable to intersect, to connect between the 3 lower points. I continue with the auxiliary contacts, and I connect the auxiliary contact on the instrument. And on the object. I connect the auxiliary contact timing over the close contact and over the opening contact. Let's go over to the mounting of the transducer. To do this, I have prepared the different parts from the ready-to-use mounting kit. The clamp, the arm, the white holder, and the transducer. I need to mount the details together. Steady. I go over to mounting the transducer in the white holder and the flex coupler at the axis. This must have a distance in between here. And the cable is connected on the other side. And now we're ready to mount it on the circuit breaker. I have connected a part from the rotary kit on a rotating point in the mechanism. This rotating point reflects the motion of the pole. I have prepared the angle so I can easily connect the transducer. I need to connect it steady with a C-clamp and adjust the angle so it's aligned and properly and steady. And I have to connect and adjust the flex coupler. I need to extend the motion cable to connect at instrument. I turn on the instrument to check that the transducer is in correct position. I go to Menu and I move to Monitor. Here I can see that the transducer is on 45%. I need it to be between 40 and 60%. And if it's not correct, I need to loosen the flex coupler again and turn the transducer a little bit so it is in this region. That is because the transducer has a gap and we want to avoid that gap during the measurement. I have one more preparations to do. I need to charge the motor. I use B10E. I put it to motor and I set it to the voltage I need. And it's going to be a little noise. After that, I put it to coil again. And I've connected the eagle with my PC. I start with creating a new object, a new breaker, and I give it a name. I select the test plan, and I need an eagle test plan, and I want to use one with motion and no resistor contact. So I select BM8012 EV. I continue with setting the stroke. I use 100 millimeters because I don't know the stroke of this transducer, so I use a simple value as 100 because it's easier to calculate if I get more information in the future. I extend the measurement time on both close and open operation. I know this breaker is slow and I need enough time to catch the whole motion, not only the timing. I save, and now I have my new object in the list. I continue with creating a new test and start with a close operation. I push new recording and select uncalibrated transducer and OK. I push measure and will continue with controlling the breaker from the analyzer. One preparation is still to be done. We need to connect over this to get a continuous plus here so we can control with the instrument. It's going to be a little bang. I turn the knob. And in a little while we will get the graph on the screen on the PC. I get the three timings, red, yellow and blue. I get the coil current, a very small one, and a motion. I will move the motion layout a little bit, just the Y scale there, so I can get it a little bit higher up in the position. I move it to position 6. So we have the motion in green. Continue by closing, saving, and doing the next operation, an open operation. New recording again, measure, and I need to turn the knob again. And that's going to be a bang. And again, here I get the timings. It opens about 45 milliseconds. And the red coil current and the green motion. I also can see here in the parameter list that I was saying wrong. It was actually about 54 milliseconds. It's easier to see it in the list format. And the maximum current was 0.5 amp. I close it and save it. And now I want to do more measurements. If this was in the real world, I would actually do 3 of each kind. But this will be the same procedure, so I close here. But what you need to know is that in this situation, I have actually only done one proper recording because my first measurement was a calibration. So this one is actually not considered a real motion measurement.
Hang on, gotta go. I've gone.
Okay. You've seen the little demonstration. Marie-Claude, have there come any more questions regarding the demonstration?
Regarding the demonstration, not yet. We I have one of someone who didn't get the answer on if that equipment can be able to measure all the tests you have been discussed about. I think that you mean the agile.
As I mentioned, the eagle measures the timing, auxiliary contact, and motion. And but I would say when you want to do contact resistance measurement, I recommend the MOM2. And if you have this vacuum, you need a unit which supplies up to kilovolts. So it's not done with an analyzer. That's a separate unit. And to do this minimum tests, you need a unit for power supply. So you need a couple of instruments to do it all. And also you need accessories like transducers and current clamps. So I can't see an instrument doing all of those measurements. Many, but not all, right?
Another question is, what test should I do on my vacuum circuit breaker more than timing and motion?
First of all, it's not always possible to do motion. Maybe you didn't mention that, but sometimes it's just not possible to connect. But you should check the auxiliary contacts, and you should do this vacuum integrity test. Maybe not every time, but as soon as you have moved or have a new circuit breaker, you should do this integrity test. And you should also check the contact resistance. So I would say analyze the test with timing and motion if possible, and static resistance micrometer test with a MOM2 or similar, like a kind of ductor. And yeah, so resistance, vacuum, and timing and motion if it's possible.
And we have another question from Terence Young. Terence, if you can unmute your microphone, we can listen to you and your question. Terence, are you still here? Normally, yes. We can hear you if you want to ask your question. And maybe no other question. Then we have a last one, which is, how often should I test my 12 kV circuit breakers?
Yeah, as I mentioned, it depends on how important it is, and also, of course, how in bad shape they are. If you have really good quality, and maybe you distribute to a residential area or something, 5 years would be enough. But if you have breakers that are complicated and you have a lot of faults, I think you should test more often. And if you have important things like maybe hospitals or yeah, like nuclear power stations and these kind of things. Also in these stations, there are 12 kV circuit breakers. But if you're like, you have a factory, how important is it? Is it, for example, some kind of oven where the material can get cold and destroy the oven? Of course, that circuit breaker is much more important than the circuit breaker which goes to the residential area next to in the same station. So even in the same station, this can vary, but every 1 to 5 years, I would say.
Another question from Fred. Is it possible to predict closed coil damage from the coil current analysis?
To detect coil, can you repeat?
Yes. Is it possible to predict closed coil damage from the coil current analysis?
Often, yes, not always, but common problem is that they get stuck and it gets like a delay in the coil current. It depends on the types, on the faults. There are also different how coils quality and also how they're mounted. If you have a coil which are mounted vertically, that tend to work much better than the ones that are mounted horizontally, because there is a moving part and that part can get stuck inside. So if it's horizontal, it's more easy they get stuck. And this kind of faults you detect in general with coil current measurement. Also bad contact in this auxiliary circuit you find with coil current measurement. I think we sort of hit an end for the day, I think. I hope you're going to be back on Thursday when I'm going to meet you again. You have a possibility.